So I also did it way back, and most of you will have solved it via the location of the columns. So just seeing the data set, it's in column position 20. But if you go back to like dplyr and its helper functions, you could have this. So in this case, so I loaded in the above step. All I did was load the data. So this is the first step. I read it directly from this thing. So this link will read it directly because we can. So it doesn't have to be in the data in your working directory. You can read it online as well. And the next step, I used select and then the in-class object, which I generate first. And then I say numerical range. And then I can have a prefix, which is item. And then I pick 13 to 24, because if you just, for example, with an example where people just use starts with, for example, item, but there's 40 items or something in this, so it would extract too many. So if you wanted to have something which has a numerical range of something which starts in a certain way or ends in a certain way, you could use those combinations in order to get what you want. So again, going back and look through those helper functions, here you could quite easily spot the columns in which they're in, and you were quite lucky because they're all nicely sorted. So 14 followed 13 and all these other things. In reality, sometimes I'll come across messy data where people haven't been clear, or they've typed item with a capital or not a capital, or all these other things. So you might have to do some creative ways in which you can use dplyr to sort of solve this type of puzzles for you. Also, you only had 67, but you can imagine if you're working with big data, you'll have 1,000 of those columns, and then you have to find out which column position it lives in, which is going to take a lot of time every single time you have to do it. So this is the shortcut, and then you have the same type of thing. So here I did skim to sort of describe what the data set looks like, and this is the same result that you hopefully got. So we had marvelous adequacy. We have an average of 0.94, and none of them dip below 0.9. And if you wanted to store it, well, this is the later thing. You could use syncs, but we'll get to that in a bit. Okay. So just to say again, also when I'm checking your assignments, there's more than one way in which I know you can solve things in R, and I'm some bits might be faster or slower, but I'll be definitely following your logic through. But sometimes it will not work. For example, if you used, in this case, if you had to pick column 13, that's a mistake because it's item 13 I was looking for to item 24. So what we can also do is we can make a nice little plot. And this is again something we've done before. Because we're interested in the strength, so we make a correlation matrix, and because everything is correlated, we can do that. And in this case, we've done it for the first 20, just in order to avoid that we get it with a very large matrix. So that's taking the column position, that's doing a correlation matrix, and this is taking the absolute. And absolute is just because we're interested in the absolute strength, and some of these items might be negatively scaled, and then our color scheme will be messed up. So if we want everything just expressed as the strength, like how strong the relationship is, we take the absolute of the correlation, right? So we don't care about the sign as to whether it's negative or positive. And then we can use core plot, and core plot is something we've used in the past to make a little thing for us. And then this is the first 20 items. This should be like the diagonal is not a perfect diagonal because we only have the 20. We only have 20 items which we selected. But you can see the size of the bubble will then give how strong the association is between those two items. So sometimes that's already useful to sort of see what's going on. So responsibleness, for example, is associated with carelessness and with disorganization. Obviously not in a positive way because they might be reversed scored. There's some association between those variables. Okay. Before we move along, I have to tell you some further terms used in factor analysis. And again, you can click this. So we use the term factor to describe the underlying latent construct causing the observed variables. So for example, intelligence, that would be an example of a factor, or introversion, extroversion, that would be an example of a factor, or openness to experience. And a factor is estimated by a linear combination out of the observed variables. In this case, for intelligence, it could be tests, like people are doing Raven's progressive matrix test, and another test like a verbal intelligence test, and they all load on intelligence. It could be, in our case, it's the items from a personality questionnaire. Yeah. And when the best fitting factors are found, you should be aware that these are not unique. There could be other things which fit your data. And it can be shown that any rotation of best fitting factors is also best fitting. This is very confusing to me, but basically because you can think of this as being a matrix being rotated into space, you can still perhaps do that with a 3x3 matrix, but basically it's all being rotated in space. It means that there's another solution which you could rotate, which also will give you a best factor solution. Don't worry too much about that. So interpretability is used so by selecting the best rotation of amongst all these equally good rotations. So what we then do is we take this matrix and we try to, for example, maximize the distances between these factors so they become more and more interpretable. So that's the rationale behind it. And so to be useful, these factors should be interpretable, and rotation of factors is used to change the interpretability of these factors. So once we've extracted factors, we will rotate them. So it doesn't really matter. You can extract them, but then you can mathematically show that you can rotate them in any possible way and still get the same solution of like the number of factors. But then in order to maximize the interpretation, to understand the loadings of each factor, we use some type of rotation method. We use factor loadings, which I just referred to as the strength to which a variable is driven or caused by the factor. So in this case, we could see, for example, if responsibility is very strongly loading on conscientiousness or not. It basically is the strength of the association between this indicator variable and this latent construct. Yeah. Factor scores or factor weights, not the same as factor loadings. So for each factor, once we've done this rotation and we've generated an intelligence score, an intelligence factor, we can assign every participant a score based on this rotated solution. And that's something we can add to our data frame, and with something which we can then use later on in our analyses. So once we've solved this factor problem, for example, for personality, we can add a personality score on each of the 5 of 6 dimensions for each participant to the data frame, and we can then use that to predict health behavior or whatever it is that we're interested in. Yeah. So commonality, that's also a term you might come across, and it's the extent to which the variability across participants is the variable is explained by sets of factors extracted in the factor analysis. So it's again a very complex term. It's basically a degree to which a variable is specific or shares different variances with other factors. Yeah. Again, this will become more clear if we actually do it. I'm not sure if I've gone into more mathy things already than Johannes has done, but the key thing is you sort of know how to interpret and what it all means. So in this case, I'm going to use a varimax rotation. Remember, there's many different ways in which you could rotate your solutions. It doesn't matter necessarily for the amount of factors you're going to get. It's going to change how interpretable the loadings are on each of those factors. And so we use varimax. It's one of the most commonly used ones. Do you use varimax with Johannes, or you don't remember? Promax, all sorts of other things. Minres, all sorts of factor rotation methods. It might have been slightly different for principal component analysis, also than for proper factor analysis. So we use the site package to do this. We say this is FA for factor analysis, the data we feed to it, and we're just going to start out by actually asking for a large number of factors. We're going to ask 8 or 9 or 10, just a very large number based on our data set. And in this case, we're going to use, this is the factor method, the rotation, and the factor analysis. And this would be the bit you would be looking to change if you had to do PCA. So I think most of the time, FA sort of tells you whether it's factor analysis or a principal component analysis. You get a bunch of output, and we're going to work our way through that output in a moment. So let's see if we can do that. So I put everything in a sink. Let's see if we can have a quick look. Yeah. So we have all of those 32 items, and the MR1, MR1 that goes up to so there are 8 of those. They're not going to be in 1, 2, 3, 4 because it's rotated. So it might be that 8 is in position 4 or something, but there should be 8 of the factors that we extracted, and we have the loadings on each of these factors. And then below we have how many of those we have, how much variation of them is explained, like how much variation is explained by each of those factors. Yeah, and so cumulatively they explain the 100% of variation of these. So this is the cumulative variance. So we explain 59%. These 8 factors explain 59% of the variance, and this is just of this 59%. How is it partitioned across those factors? Yeah. So yes. So lots of things to look at, but it will become clearer when we do it. You can already see that some things are loading quite strongly on this first factor, for example, like minus 0.84 and like 0.79. So these are strengths, and like a higher number in absolute terms means a stronger association. So you might already be guessing that some of these things might be relating to introversion, extroversion, because we have quiet, we have something to do with shy, and we have something to do with talkative and distant. So that might be looking into the introversion, extroversion continuum. Yeah. So that was just a bunch of output which you get. Now, we need to determine, so we just call a large number of factors the first step to sort of get an idea as to what's going on. But how do we determine if it's 3, 4, 5, 6, 7, 2, 1? That's the next step. So, unfortunately, you have choice overload. There are many, many different options in which people in the past have said, this is how we determine how many factors it is. So you could, so this is just a list from Ravel, and you could extract factors until the chi-square of the residual matrix is not significant. You could extract factors until the change in chi-square from factor n to factor n plus 1 is not significant. You could extract until the eigenvalues in the real data are less than the corresponding eigenvalues of a random data set of the same size. You could plot the magnitude of the subsequent eigenvalues and apply a scree test to basically see if it's dropping down. You could extract factors as long as they're interpretable. So you could do 10, 12, as long as you can put names to them, it's all good. You could use something which is known as the very simple structure criterion. You could use something which is known as Volzer's minimum average partial criterion. And you might have heard of this. This is Kaiser criterion. Did you hear about that from Johannes? This is basically eigenvalues larger than 1. So choice overload. So like way too thing. Like each has its advantages and disadvantages. And even though you might read, you might see this the most common in the literature, this is probably the poorest criterion in order to select your case. So I wish I could say always do this or always do that, but there is no consensus in this case. So I'm just going to run you through some of the most common things. So also part of the output already, but I use the min-res extraction method again, and we can use parallel analysis where it prints it here, and that tells you the number of 5 factors. So it's basically using this type of thing where we make random data sets and basically see random data sets are basically junk, and basically we want to have more factors in our real data set than in the junky data set. Yeah. And so you could see in this sort of chart, you could see the simulated data or resampled data, and you can see how that behaves compared to your actual data. Yeah. And so you can then do some maths to it, and that's what it will print. Unfortunately, it's not printed everywhere, but you can see where you compare. So here, this is where the red lines are touching the blue triangle. So you could say here we can no longer differentiate between our simulated data set and the real data set. So we're going to call it quits at 5. Yeah. So that's quite nice because we already know it's the big 5. So that's our good news perhaps for us. So that's one criterion which people have used. So basically you simulate lots of data sets and then you see what the pattern of factor structure is in there, and you see how it differs from your real data set. That's the actual output. So this is where I get this 5 number from, and then it has the eigenvalues for those factors, the eigenvalues for simulated factors, and so you have some more things also as output. So these ones still, you remember the eigenvalues 1 criterion, 1, 2, 3, 4, 5. This one still scrapes by being above 1, and you can see that these are much lower, and you can see also where they then start touching on where would be the cutoff point. Yeah. So Kaiser criterion, we saw that on the graph. We can also extract them all from our object by just using the dollar sign, we can say fa.values, and then it will print the eigenvalues, and we can see this is the 1.02 that we had here. So in this case, we can also see it on the graph because we had this line where this is the 1 line, and this triangle is sort of still above, slightly above 1. So that's where we would draw the cutoff, and so also the Kaiser criterion here would say we would extract 5 factors. So perhaps I should give you a break here until 10, and then we'll continue with some more factor analysis stuff, and you're going to also do it on that teacher data set. Okay? Lots of things to digest. Don't worry, you have time to rehash it. Again, most of the thing is just applying it and not worrying too much about what eigenvalues mean or rotation of matrices. So, okay, see you at 10.